scientific analysis. How people like the pizza. Yeah.
Oh yeah, so you're not eating pizza anymore, are you, Alex?
No pizza for me.
Yeah, no, see that. Oh look, there's more guys. That's a good discussion.
Oh yeah.
Don't you think
He'd be
it's,
great.
yeah, I think our chances are good to get him.
So, what kind of tank is it?
You know, I think he would, I think it's looking like.
Come on, you can pick out freaking cruise ships by like, you know, an corner offside of. That was still amazing.
Those really weird
For the,
World War I ones with the tread that went
for, look at the house.
We only know World War II.
Just get the.
So this was funny.
See, the deal on
So I
that
was
one
at
is his
PSHE
wife
last year in Vancouver.
came from LA.
My bathroom was actually overlooking sort of this,
Never really
like this
been
little bay area where they park cruise ships. And I posted that, joking about how, you know, my toilet literally has windows
Oh,
right
we
next to
didn't
it.
interrupt him.
And Kristen Wheeler posted and said, hey, you know, did you get a picture of that cruise? There's a cruise ship back this today or whatever or something. And I was like, what was it?
And after, so I think we can go ahead and get started.
Alan goes, well, that's neat. That was the
Welcome
Princess.
everyone, Tools and Technology Seminar Series.
This isn't it?
Ryan,
Sorry.
you're starting.
You caught me mid-story.
Sorry. So as you probably noticed, we are testing out a new pizza vendor. Feedback is welcome, so please feel free to let me know after the seminar or email me with your opinion on it. It is just sort of a trial run, so based on feedback, we'll decide whether or not to stick with this or go back to Pizza House. All right, so today I'm pleased to present our speaker, Karandeep Singh, who is Clinical Assistant Professor of the Department of Learning Health Sciences, and he's going to talk to us about R and machine learning.
All right, great, welcome.
Thanks for having me. And just so I know, these CCMB signs are outdated, right? You guys are DCMB now?
Yes.
Since when? Just
Well, we still have a center.
oh, so it's both. So it's
both.
so it's a department and a center.
The center's house
Okay.
and the department, yeah.
Okay. Just curious that I would ask. So anyways, I'm excited to be here. Thanks for inviting me. And I am planning to talk about and mainly demonstrating how to do supervised machine learning in R. And the focus for the first part of the talk will be talking about just figuring out in the room kind of what the level of experience is with supervised machine learning. So we'll kind of keep it interactive and do some Q&A. And then we'll dive into actually doing it and seeing what things we can do and what MLR can help us figure out from a variety of models. So a little bit about me before I do this slide. I'm relatively recent faculty, recently joined faculty member in the Department of Learning Health Sciences, which is also housed in the med school. I was previously here for undergrad med school, left to sunny LA, then to frigid Boston, and then I'm back here. So did training in a couple of places. Several weeks of the year I practice nephrology in the hospital, but most of my time is spent doing kind of informatics research, in which I use tools primarily in R. So just to, the other thing I'll mention is that I teach a class here, LHS 610, which is a intro data science course where we teach R, and it specifically relates to health. So we deal with a lot of health-related issues and also get into some of this stuff in the course towards the end. So just so I know who's in the room, who's used R? Okay.
Oh, wow.
How about Python? Okay. How about SAS?
Oh, yeah, actually,
Okay.
kind of embarrassing.
So I won't do Stata and SPSS, but just wanted to get a flavor for what people's kind of experiences with various tools. How many people in the room are familiar with machine learning? Okay. And how many people in the room know the difference between supervised and unsupervised machine learning? Okay. How many people have ever used regression for an analysis? So I'm not talking machine learning, but just plain old regression to figure things out. Okay. And then how about machine learning algorithm for analysis for something you've done? Okay. So given all the hands that have gone up, there may be times where I see heads nodding and I'll move forward. But I still want to have some discussions depending on where it's needed. So, but it's good to see the level of experience in the room. And I didn't ask this, but how many people have used MLR in R? And how many people have used Caret in R? Okay, so just curious. Those are two packages that people use for machine learning. So we'll do like a very brief overview of machine learning. I'll probably skip some of these slides. There's some questions we'll do around what data set we're going to look at, and we're actually going to try to work through an example in the next hour. I'll do a brief introduction to our MLR, and then we'll pretty much dive into and try to build a model and see if we can predict diabetes, having data from a population of Pima Indian women. And this is a pretty famous / publicly available data set. So it's a data set you may have encountered at some point. But if not, we'll actually get into it a little bit, and I'll show you what's in there. And we'll try to figure out, even before we build the model, do we think our model will do well or not? And how do we define success? So machine learning, is an area of study where primarily we're trying to learn by example. This is unlike the idea that we're going to tell the model what to do in advance. So this is not a set of rules. This is show examples and have this machine spit out an algorithm for how it's understanding that information. The phrase is coined by Arthur Samuel at Stanford, who wrote his first self-learning program to play checkers in 1959. And so unsupervised machine learning is where we don't have an outcome, and so we're really just trying to understand the relationship between a set of variables. And so we often do this kind of very early on when we have a very high-dimensional data set, just trying to figure out, how are things related to one another. And we may want to do this to define subgroups or subtypes where we're clustering observations or like rows in the data. Or we might want to cluster variables and try to figure out which variables carry similar information. So if you are working with like single nucleotide polymorphisms, you want to figure out which SNPs are carrying similar information when it comes to relating it to a phenotype. Is an example that might be familiar to you. Supervised machine learning, which is primarily the example we'll be running through today, is where you have a set of predictors and outcome, and really you want to learn the relationship between the predictors and the outcome. And a successful supervised model should be able to generalize. And who knows what I mean by generalize? Feel free to just start talking. So back there. So wait, hand in the back. Did you say you're familiar with generalize? Yeah. So, and I realize you're eating pizza. So. So.
Ricardo can answer it.
So you can apply that to other data sets that you haven't seen before and make sure not to repeat it.
Exactly. So you want to make sure that the model is not just memorizing the data that you show to it, so that if you show it data that's generated in a similar way, that it's going to fit that data well too. Because a bad model is one that will just memorize the data in hand. It'll do perfectly on your data, but it will not perform well on new data. And so it should be able to present, correctly predict the outcome, not just on its own data set, but really the measure of success is how it does on new data with consistency and not just the original data. And so we call the original data oftentimes is the training set data, and that new data we kind of often lump together as kind of test set data that we set aside to see how it's going to do on that. And how it does on that is how we think it will do on other data that we get down the road that we don't have access to yet. So this is a little bit of a detour, but for those of you who said that you have done regression analysis, people do regression analysis for kind of two reasons. So when you were using regression in something that you were working on, what was the reason that you were using regression? What was the value, or what was the number that was kind of most relevant to whether you were going to get excited or not? So it could be a certain type of value that starts with a letter, or it could be R squared. So, or it could be something that's squared. Yeah. So, so the reason, one of the reasons we do regression analyses is that we want to test a hypothesis. And so sometimes we have outcome, we have a set of predictors, and really only one of those predictors is one that we care about, and the other predictors are kind of our covariates or potential confounders. And so in epidemiology, we frequently will use a regression analysis to really figure out what's the relationship between one predictor and an outcome, adjusting for other predictors that we think are confounding that relationship between that exposure and the outcome. And so an example of this is, what are risk factors for heart disease? And if we have one in mind and we want to test it, we would put that variable, in the model. We would put other things like age, sex, things that we think, cholesterol levels that we think might confound that relationship, and then see what that relationship is with the outcome. And then here, R squared. And so, the other thing we get excited about is if our model actually fits the data well. And so if you have, if you build this model to test a hypothesis and it turns out that your R squared is horrible, R squared is that metric that helps us figure out, is this model even a good representation of the data? And if it's, R squared is very low, it's not high, then, we kind of say this is not a good model to begin with, so we can't really do much with it. And so an example would be if you've got a set of SNPs, how well can you predict the onset of heart disease? And so there was this paper in the European Heart Journal. Scroll down here. And so they actually looked at 50,000 SNPs, and they built a genome risk score where they used all of these SNPs to kind of come up with a risk profile. And they compared it to kind of Framingham risk score, which is a set of clinical predictors, and figured out that genomic data carries additional value beyond clinical risk factors, which is not surprising. But the idea here is that they didn't really look to see which SNP is important. That was kind of done as part of the modeling process, but that wasn't the key intent of this analysis. The key intent was to build that model and see how well can we actually predict that outcome. And so we talked about how we measure that a supervised machine learning model actually fits data well. With regression, so actually I'll get to that next slide. So regression is actually a type of supervised machine learning model. So, but supervised machine learning models in general we don't use to evaluate or test hypotheses. And so logistic regression is a type of classification model. We're trying to predict an outcome that's yes or no, or it's multiple categories. Linear regression is what we call a regression algorithm. And just note that if you've used regression in multiple senses in machine learning world, people often use regression to mean predicting a numeric outcome, and they use classification to mean predicting a categorical outcome or a class outcome. So quality of fit in linear regression is often R squared. In logistic regression, it's AIC or ICACI information criterion. And in supervised machine learning, we tend to not look at these at all, and we tend to look at cross-validation performance. So before I get to just that, and I'm only doing this because we're going to show cross-validation performance, and I want to make sure that you guys have kind of a working understanding if you haven't dealt with it before. Who R squared? Have you? I'm not going to ask you to explain what it is, but have you dealt with R squared before?
Okay.
Everyone? Yes, I see a lot of heads nodding. I know, but
Never know.
when I walk in with assumptions, they always get broken. So thankfully, you guys have not. How about AIC? You guys do a lot of logistic regression. Okay, and that's GWAS and things like that. Obviously, you guys are dealing with. There was p-values, but so you guys have dealt with these things. Cross-validation performance. How many of you have dealt with that? Okay, so fewer heads nodding than for the last two. And so the question I have is, why can't we use R squared or AIC for looking at machine learning algorithms? And does anyone want to venture kind of idea, especially if you're familiar with cross-validation, why we don't just use R squared? So R squared is where we look at the residuals, the errors, we square those. We look at the total variance of our variables, we square those. We take a ratio, we subtract from 1, and basically we end up with this number. And if it's 1, that's really good. If it's, the lower it is from 1, the worse it is. And so why don't we just look at R squared? Like if I built a model that had an R squared of 1 that was a machine learning model, why not get excited about that? Whereas I would get really excited if I had a regression model that would do that. Potentially get excited, not with some conditions. You could be overfitting, yeah. So we know up front that linear and logistic regression models are rigid models. So once the variables and any interaction terms that you put in there have been kind of specified, your work is done. And so there's nothing else to do. You can. The main question you always have is, do you add additional variables? Do you take additional variables away? And do you have kind of a parsimonious model that doesn't have too many things in it? But those are kind of the battles that you're having in your head as you're thinking about, do I have a good logistic or linear regression model? But most machine learning algorithms have these additional things called tuning parameters. These are little knobs and dials you can turn that are not pre-specified. So oftentimes they'll have defaults that are kind of reasonable defaults, but you can change those. And so once you build your model, you're not done yet. And so you can continue to play with the model and adjust the model in oftentimes hundreds of ways when you look at the kind of grid of all the different things you could do. And so when you are adjusting the model and making little changes, you can get improvements in R squared that actually don't have any meaning to new data. So they are just fitting your training data better and better and better without necessarily a clear implication that it will fit a new data set very well. So because it's such many machine learning models are very flexible models. They're not lines. They can model very complex shapes. We make sure that we have a sanity check, which is we want to see how it does on data that the model hasn't seen before. And so if we just were to rely on these things, we would overfit. And so that's often our main concern when we're fitting models is we don't want to overfit. So basically the steps that we're going to walk through in R and MLR are the following. So typically when we're thinking about modeling something in machine learning, we set aside a part of our data as our test data. And what's the rule about the test data? If there was like a rule number 1, like Fight Club, what would be the rule for test data? So that is not that is controversial. So it doesn't necessarily have to be randomly selected. And the reason I say that is, if you're building a model with a set of like patients seen in clinic, you might actually want to not do it randomly, but actually keep some clinics that are separate as your test set, because you want to see how real life practice variations affect care and outcomes. So just to have so if you were to apply this to a new clinic, you wouldn't want to have patients leaking in that reflect the practice patterns of the clinicians in both the training and test set. It's even more basic than that.
That you must not include any data from the training set.
Yeah. So do not touch the test data. So once you've set this aside, so you can't have leak between the two. So you can't have training data that goes in the test data set, and the test data that goes in training. So they have to be separate. But once you've separated them, basically set this aside. Do not look at it. And we're going to use it at the very end to figure out how well we think our model is going to generalize. So then we select a model, and many people, depending on what tradition they come from, are going to have certain models that they're kind of attached to. So deep neural networks is something that in computer science and I think in general people are very excited about. In statistical world, oftentimes what I use is random forest models, and so I think this is kind of sometimes an a priori decision. Sometimes you actually can try a couple and see what fits the data well in a kind of simple, but also is a simplistic model and runs fast. And then so now you take a part of your training data. So this is not the test data. This is your training data. And you take a part of that. We call that the training set. And we train the data on the training set. And so now there's a part of our training data that's left over that is our test set, not to be confused with the test data. So this is the test set still within the training data that we're going to measure the performance on. And then we adjust our tuning parameters and kind of repeat this last two steps until we come up with a model that we're happy with. It is confusing. So some people call that holdout data to separate this term. Some people call that a validation set to separate this term. There is not a clear consensus on what that should be called. So I recognize it's confusing, but if you look, this is the most common way I've seen it, is people talk about training data, test data, and then within the training data, a training set and a test set. But for the sake of ease, we can call this holdout data.
Terminology.
Yeah. So this is, we can call this holdout data because that's another way, but there's not a clear-cut standard across the board of how people describe that. So for today, I think we can call that holdout data so that you won't have to kind of go back and forth in your head.
Sometimes I also hear about developmental data or development something like that.
So
What is the difference between training data?
it's the same. So training data, so a training cohort, a derivation cohort, or a development cohort are all the same. That's the cohort of data you're going to use to develop and kind of evaluate your model before you settle on a final model. The test data, validation data, or holdout data is that data that you have locked away behind in a safe that you'll only pull out at the very end once you've selected all the different all the different tuning parameters that you want to use, and just evaluate at the very end and see how well did I do. And the reason you lock it away is if you don't lock it away and you keep looking back at it, you're going to start to learn aspects of that data that will make you think you're doing really well. And then if you got another new data set given to you, you wouldn't do as well as you expected on that. So this is to measure how, the test data or the holdout data is kind of that sacred, how well is my model actually doing? And there's a bunch of different ways people do this. Some people repeat this whole experiment with different training test splits, but that's kind of the most simplistic thing that people will do.
Yeah, just for background, there's a 2012 report from the National Academy of Sciences I was involved in called The Evolution of Translational Omics, Lessons Learned, Path Forward. And it responded to a very awkward situation where overfitting was extreme and claims of cancer treatment responses were invalid. A small item in that report was the distinction made between confirmation and validation. I think what you just described, where you take one batch of data, the word batch for a reason, and you take part of it for the development or derivation of training, and the other part held out for the test, is still quite a preliminary step.
Yeah.
Because you have no variables for all the other samples that you could be taking for a similar analysis. The best you can say about that situation is that you confirm findings of the training set. Better is to do a reanalysis, same or similar data, make sure it confirms. But validation should have a higher standard. Validation should be from a different sampling at a different time, with the batch issues of timing and people, labs, and all the rest.
So some people call this internal and external validation. So if I were to call it that, I would say even this final this kind of holdout data is internal validation, and external validation is get a whole new data set from a different source where there's kind of other things in play to really see how well, because really the question is how well it generalizes. So, okay. So once you've selected your final model and your tuning parameters, go ahead and train one final model using all of the training data, and now evaluate on that test data or the holdout data that we left out and see how well it does, because that's our, what we're going to hang our hat on is kind of our internal validation. So why split the training data into two pieces? Why not just use all the training data and train, and then measure performance on the training data? Half of my questions have the same answer, so overfitting. so if you have a model that can perfectly memorize training data, that's otherwise not a very smart model, it will spit back out to you the correct answers for your training data, but will not then perform well. So this is the idea that although we've set aside a test data set or a holdout data set, we're still taking half the training data and training, we're calling the training set, and then evaluating on a test set.
So is half the ratio you recommend?
Half is not what I recommend, but that's what I'm starting with, and we'll get to what is kind of recommended. So So since the model is only trained on the training part of that training data, the training set, the performance on the test set within the training data should still be some measurement of generalization. Now, if we actually split it into exactly half, which one should be our training set? Which one should be our test set? Shouldn't we just, take turns and do both? So train on one, test on the other, train on this one, test back on the first one. So in fact, we should. And if we did that, that's actually called two-fold cross-validation. So if we just split it in half, that's kind of called that's the derivation validation approach. But as much as we can, we typically want to do cross-validation. So if we cut it in half, that's called two-fold cross-validation. But if we cut it into two halves, we're only using 50% of the training data to learn. So isn't that a problem? Meaning, we already set aside a test data. Now we've cut our training data in half, and now we're down to very little data that is actually being used to train. What are these important relationships that we're missing because we're only learning from?
Well, this is because you're creating a test set within the training set.
That's true.
Why is that necessary?
Because why is it necessary to create a test set within the training data?
When you already have a test set.
Because we can't touch that yet. The reason we can't touch that is because we're going to turn a bunch of knobs, and we don't want to see how the knobs affect the test set. Test data. So we want to see how the knobs affect the test set within the training data, because that will at least to some extent prevent overfitting. And the next slide is a visual slide. I realize there's a lot of words, so let me just demonstrate this visually. So if this is our complete data set, we say this is our training data, that's our test data. We set that aside. What people often do is they'll actually cut this training data into 5 or 10 pieces. So they won't just do 2 pieces. And in this example, they actually show 4 pieces. And then what they'll do is they'll train with this 3/4, test here, train with these 3/4, test here, and do that down here. Measure the accuracy or error in each of these folds, average them, and that's how well you expect it to do on the test data. I realize that's kind of maybe not intuitive. An extreme case of this is where you actually leave one example out and train with every other example and just evaluate that one example, and that's called leave one out cross-validation.
Then you rotate through the whole set.
Yeah, so either way you're rotating through the whole set, but you can either do kind of for efficiency's sake cut it into 5 or 10. At the extreme, you can do leave one out. And the idea is you're going to turn these knobs, and your cross-validation performance may improve. It's possible your test data performance won't, but you want to pick your model before you ever look at that, so that you're not learning your test data that you're not supposed to look at.
Isn't the variance greater
if you leave one out?
Is smaller depending how many folds you use?
It is. So actually, if you do leave one out, that is high variance but low bias. And so there is this bias variance trade-off. So many people, including some of the statisticians kind of first described this, have said 5-fold or 10-fold is kind of just accepted as a near standard because it's kind of it's a good trade-off between bias and variance. Some people will even do repeated 5-fold cross-validation. Well, they'll do this once, they'll take different cuts, do this again, different cuts, do it again.
So there's another variable, which is the number of specimens versus the number of variables.
True.
Is that in this model too?
Every variable goes into every one of these folds because this. So typically that's not used to decide folds, but it's mainly that if each patient or each person is a row in the data, all we're doing is splitting the rows into these folds, but all the columns stay. I mean, unless you specifically wanted to exclude columns, or you're doing filtering on the columns based on some criteria. So that's, I think, pretty much all the background I have to get to just actually running through code and showing you some graphs and trying to do this kind of ourselves. But any questions so far? Yes?
So one thing we've been thinking about is often we pair that the portion of cases and controls. So when you're testing, you don't want to test on, say, an even distribution because it's not realistic, or to test on the distribution not being practiced. So that's important, I guess, for a test set. Is that also important for the cross-validation step as well?
So the question is the So one thing you can do is you can evenly distribute based on a certain characteristic throughout the folds. Is that what you're saying, or are you talking about imbalanced classes?
Imbalanced classes, I think.
Okay, so imbalanced classes is the idea that let's say we have something that's really rare. So we're trying to measure like a occurrence of a rare disease, and so we want to do tenfold cross validation, but only 20 people have it. So there's two issues at play here. One is that if we just randomly allocate those 20, chances are some folds will get none. So oftentimes when we have a really rare thing we're trying to model, we actually will stratify to make sure that rare cases end up evenly kind of in each fold, so that you actually can run this. Otherwise, you can't get an accurate measure of what accuracy means when there's no cases. The other part of that is that if it's really rare, it might not learn that rare example very well. And so people often use downsampling or upsampling, where they either generate repeated examples, they basically kind of upsample the rare class to make it more even with the other class, or they downsample the other class so that if there's 20 people with a rare disease, 100 people without the rare disease, you might cut out 80 people, so it's 20 and 20. But
when you validate it, you want to make sure that the distribution is realistic as well.
in your test set, you absolutely want to make sure the distribution reflects real life. In the training set, there are papers that talk about upsampling and downsampling as possibly helping you better learn a rare class, but it's not like, and then there's even something called smote sampling, which is artificially generating new kind of small classes. I think that's probably beyond what we're going to talk about today, but it exists, and it's a thing that people worry about.
Don't worry about total time and slide number.
I realize that. So, but this will go quick, I think, actually, because there's a less discussion here. So I do want to just make sure this is just that we're all on the same page with this kind of stuff. What kind of a task is predicting diabetes? Classification or regression? Just say it out loud. Classification. Okay. If we develop a model using our training data, it's 99% accurate on cross-validation, but only 80% accurate on the test or holdout data. What happened? Overfit. Okay. Let's say a model is 99% accurate on both the training data and test data. Is this good? Are we happy? Depends. If only 1% of people have HIV and you're building a model that models HIV, if you're 99% accurate, you're no better than just saying no one has HIV. So if you build a model that says no one has HIV, that model is 99% accurate. So in reality, we actually often don't use accuracy as a good measure. We often use things like error under the curve. I won't get into that today, and we'll use accuracy for today. But just realize, always set your baseline worst accuracy based on the largest class that's there. So if, and I think for the example we're going to do, 66% of people are diabetics. So the worst accuracy a model should have is 66%. If it's less than that, that's actually worse than just saying everyone is diabetic. Okay. And then let's say your model thinks the probability of diabetes is 51%. What should it call it? Should it call it diabetes or no? This gets into a whole thing we won't get into, which is area under the curve and figuring out what is your sensitivity and specificity at each cutoff level. So for the case of today, we're going to call this diabetes, but just realize in real life, you can set your threshold, and that depends a lot on what you're trying to predict and what the purpose of your model is. Is it a screening model? Prevalence, and also is it a screening model or is it a confirmation model? And so you always want to understand, when you pick your cutoff, what it's intended to do. Okay, so I'm going to skip this stuff since you guys already know R. And I'm going to skip this stuff, but just to let you know, this Caret and MLR are the two meta packages that wrap hundreds of other packages. And Caret's probably more well-known, but I think MLR is actually more powerful. I use both, but I've switched over to MLR primarily. And also because MLR actually wraps Caret. So things that Caret can do, MLR can't, you can do it in MLR. Okay. So this is the data set we're going to look at, which is the Pima Indian data set. There's actually 3 data sets, Pima TR, Pima TR2, which we'll ignore, and Pima TE. They actually divided this into a training and test set. TR is training and TE is test set. So we're only going to use TR to train today. And then at the very end, we'll evaluate on TE. These are the variables. There's actually not that many. They all pretty much fit on the slide. So number of pregnancies, glucose, concentration, blood pressure, skin fold thickness in the triceps, body mass index. This is a family history kind of continuous function from 0 to 1, age, and then this is the outcome. Were they then diagnosed with diabetes or not when they had kind of down the road?
So these are all kind of physiological measures. I mean, could you add heterogeneous?
Absolutely. And these are all numeric, but you can add categoricals, ordinals. I mean, anything you can think of, you can.
But I thought it would be good to.
Yes, absolutely. And most of my stuff, I look at predictors from notes. So most of my things are like concepts from notes. And so I usually have like 7,000 of these, so I can't fit them on a slide. So we're going to load some essential packages, and I can send, this is just to show you the code. We're loading the data set. This will work. It just gets blocked as a pop-up. So you have to hit Control-R or F5, and then it sometimes works. So let's see. So this is just going to view the first few rows of the training data. There we go. So this is basically the first, one of 200 rows, and so there's really 200 women in the training set. Interestingly, there's actually more women in the test set, 332, but usually we split it the other way. But that's just how this was, and it may have been the way they actually collected the data. The test set may have been actually collected at a later time. And so this is what we're trying to predict.
How do you get a pedigree value greater than 1? You said it was 0 to 1.
I could be off on that. Is it? I'm wrong on that. It's a function. I don't know if it's 0 to 1, but it's. I'll show you the graph so we can see what the normal values are. But it's higher means like more family history, and it's like a function based on a variety of questions that they turn into a single question. So are the outcomes separable? This is something that we often do before we ever build a model. So if these are the non-diabetics, these are diabetics, and you don't have to believe these if you don't believe in these for table 1s, but you can see that there's more pregnancies in the diabetics, higher glucose, which is not surprising. So we think that even just looking at the first couple of predictors, this is going to be probably separable. If we view this graphically, we can look at this as a kind of density separation. And so this is using ggplot. And so I would say, if the peaks are where most of the data is, and this is yellow is yes, and red and green is no, then the peak for BMI is clearly higher, and this is bimodal for non-diabetics. But there's one peak that's definitely lower. Glucose, you can see that the peaks are clearly far apart. So we think there's going to be some, we can't draw a perfect line because they're not completely separate, but potentially between all these variables here, we may be able to separate. This looks almost overlapping. I would say that looks very close to overlapping, although it's, so ignoring p-values here, a lot of the data is in the same boat here, so probably it's not going to be that helpful to separate.
Do they have explanations? Is it like misdiagnosis? If you've got under glucose, under the normal, that goes way out to the right.
That could be because you ate.
Oh, okay.
Because you can have a blood sugar 200 if you're asymptomatic. It technically doesn't count as diabetes if you just ate.
Usually
that's probably insulin deficiency. That's true. I don't know how they did these ones though, and so I have to look and see. But you're right. You have to wonder about data quality issues. Okay, so we need to tell MLR what kind of task, what data set, what model, what measure. And what do we want to do? Do we want to do cross-validation? Are we ready to train that final model? Or are we ready to benchmark? And I'm going to basically skip to, so we tell it, here's our data set. We want to use logistic regression. We want to do 5-fold cross-validation. We always set a random number seed so we get the same result when it does resampling. And we just tell it we want accuracy as our kind of final measure. And then we ask it what happened. And it tells us that on the 5-fold cross-validation, the accuracy on average was 75%. And so we know that just based on the split of the data, 66 is the worst you could get. So 75 is better than that. And how good is that is something that we're going to kind of grapple with a little bit.
For that 25% of error, we want to distinguish type 1 and type 2 error, with differential penalty to
You can, and so if you look at a 2x2 table of where it messed up, you can decide based on if you have a cost in mind, a cost function for what type of error is worse. You could look at that and make it. But again, this is assuming a 50% threshold, and I could move that threshold if I wanted to. And so this diagonal is good, that diagonal is bad, because that's where the predictions don't match up with the truth. And there's 200 there because when you do 5 folds, you end up getting the whole training set. And in machine learning, we call that a confusion matrix. I know in epidemiology, it's like a 2x2 table, or there's other phrases for it. So, and then can we tune the logistic regression model? And we ask MLR, can we? And it says you can't, which we knew that. We can't tune it. That's why when we build it, we're done. Nearest neighbors is another one that sometimes people use. So it's where you try to look for points in the data that are based on Euclidean distance are close to your points. And oftentimes people use a kind of 5 or 7 as a standard. And so this algorithm uses 7 as a default. And if you do this and do the 5-fold resampling, you get 70% accuracy. So worse than logistic regression. And so then we ask it, and then I'll skip over this. So then we can ask it, can we tune this model? And there's actually a whole bunch of things we can tune. We can tune the K, the distance, the kernel scale. And if you're familiar with it, you can try doing these on your own. But one nice thing you can do is you can actually ask Carrot through MLR, I want to try 5 different things. What should I try? What's reasonable? And the author of the Carrot package, Max Kuhn, who also wrote a textbook on this and now actually works for our studio, has a function that can figure that out. And so if you want to try 5 different values, it says focus on K and try 5, 7, 9, 11, 13. So now we can go back and try tuning. And so we make this, so we redefine our learner as something that's wrapped with a tuning thing. We basically run the same code with the only addition being that we're going to extract the tuning result.
Excuse me.
Yeah.
Let me ask you a question.
Yeah.
But since you have 2 classes, diabetic, why would you pick a K of 5, 7, 9?
How much K would you pick?
Aren't you looking for 2 groups?
So what you're doing is this. You're not looking at the outcome. What a k-nearest neighborhood model is doing is just saying, look at all the predictors and measuring Euclidean distance that's standardized. For, where are my nearest neighbors? So I look at my 5 neighbors and I have them vote. So I ask my 5 neighbors, are you diabetic? Yes, 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 no, no. You're diabetic. So if my neighbors around me are diabetic, I must be diabetic is the idea. So it's not clear how many neighbors to actually pick.
Okay, so it's the number of neighbors.
Yes, yeah, the K is the number of neighbors, yeah. But your neighbors can only be one of 2 classes. So this is like, you can think of this as Redfin. Like you're trying to figure out how much does my house cost? Well, let me ask my neighbors, and then I'll kind of extrapolate. But how many neighbors should I look at? Should I look at the whole subdivision? Should I look at 2 streets down? So we can get this, and basically what this will show you is that the question I have is, do you get excited about these different values of the tuning parameter? And so we knew that at 7 we got a 70% accuracy. At 5 we get 70.3, yay. Here we get 70.3. We're not really that excited. I mean, yes, there's a tuning parameter, and maybe we could try more values. Maybe that's what part of the issue. But this is seemingly not getting us there. And nearest neighbors doesn't have weighting, meaning it doesn't know what's important, what's not. It's trying to just find the closest neighbors. And sometimes in the predictor space, it doesn't make any sense because one characteristic is much more important than the others, and so you need to consider that one a lot more important, more seriously than the others.
It also doesn't make sense to carry these estimates to 7 significant figures.
That's true. That's my laziness and not rounding, and also getting the code to fit on page. And if you're looking at this stuff and wondering what that is, if you know R, that's a pipe, and so it's basically, this is becoming the first argument of that, is becoming the first argument of that. And a lot of people now who use R will run piped code. So if this is new to you, that's why it looks weird. So we can do a conditional inference tree and basically get a similar thing. Let's see, how do we do? We get 69.5. We're not excited. We're going to skip this. We'll skip this because we're not going to get that excited. So you're starting to notice a pattern. We haven't touched the test data yet. We're still on our cross-validation and our training data. Are we ready to select a model? Well, we only tried a couple of them. Maybe we actually want to try all of them. And so what if we want to try multiple models? What if we want to take advantage of parallel processing and like make sure that each core is running a model separately? So what we can do is we can tell MLR. Task is the name of that pima.tr task. So I can say, tell me every model I could possibly run. And so there's actually 77 models that I could run if I wanted to. So yesterday I decided to just run them all. And so ignoring this page, there's a benchmark command that lets you just run whatever you want. And I said, run every model that I could possibly run on this, recognizing that it's not tuned. And so this is accuracy. Here's every single model on the x-axis that I could possibly run. And so obviously, this is cross-validation, so I want a narrow band so that each fold it did well in. I want bands that are higher. And if this is too hard to read, you can turn this into a nice table. Oops, 1 second. And it turns out that naive.
Definitely better than 0.70.
So we're better here, yeah. So 0.78 is kind of the quote-unquote best we got for cross-validation that was untuned. And just as importantly, it's important to know that we go to the last page here. There's like a model here that's getting 34% accuracy. Now that model, you might want to just flip the predictions and it might actually do okay. But there are plenty of models that are doing just as good as guessing, and so we're not super excited about those necessarily.
So how much separation in numbers is significant between those different models? You get a 0.78 and a 0.77.
There actually technically is a p-value that you can use to test that. I never do, and I would say it's not really taken seriously. The higher accuracy you're at, the harder it is to get better. So like 0.66 to 0.68 should be much easier than 0.92 to 0.94. And people typically use area under the curve. They don't. People don't use accuracy usually because of this issue of class imbalance. Scientific papers get published around 0.02 better if it's already really high. People get really excited about that. And like an image classification, like 0.02 better than what's out there is like for area under the curve is like phenomenal because people are already doing massive computational things and already are at like 0.93 accuracy or area under the curve. So recognizing that we got 2 minutes left, I'm gonna we're close actually, but basically now I trained I trained 3 of those top models: naive Bayes, conditional forest, and GLMNet, and basically said let's test them on the test set now, which up until now we were not touching. So now I've tested them, and I said we should pick one model. We cheated, we picked 3. But it's okay to pick 2 or 3. It's just not good to pick all of them and try that again. And so actually, the GLMNet model, which is actually just a linear model that's adjusted, tuned with a parameter that adjusts all the coefficients downwards, actually has the best performance at 80% in the test set, even though it wasn't the best one in the original one. So we can't now say we're gonna pick this one. But if we're going to publish a paper,
Third best out of
it was third best originally, but in the test set, actually is the best. But recognize that this is not that different. But this actually is significant. And if you really wanted to believe this, you might want to repeat this whole thing with taking a different split of your test set, doing repeated cross-validation. And so, what does the naive model, Bayes model, see as important? This is kind of a question. And we know in linear regression we have coefficients to look at. Here what we can do is we can randomly permute each of the variables, and see how much permuting any variable messes up the final prediction. If a variable is not important, you permute it, and the prediction should stay the same. And so based on that concept, naive Bayes thinks glucose is the most important.
Surprise here is BMI.
BMI is lower, much lower. And interestingly, I won't go through it, but these different, actually it loads, great. So, and here it's fourth, and that might be because BMI also has a peak.
Fancy analysis, all the genetic variant analysis, it comes down to fasting glucose.
Pretty much. Now, I mean, granted, we don't have the PEDS is not a genetic, it's a family history marker. But yeah. And then, so that was one question: is how do you figure out what's important in a model? You can permute, and that you can apply that to anything. Deep neural net, whatever. The other question that comes up is, given age on the x-axis and BMI, how would you split the data? How does the model see that? And so, if yellow is the options were red, green, and yellow, green. So I apologize. I went away from red, green, but I didn't do much better. So if yes is yellow and no is, I might pick something like this, or maybe even a line right here where all the yellows are primarily here, most of the greens are here, and there's going to be something. I'm going to make some mistakes regardless of how I draw that boundary. And you can see naive Bayes actually draws it as a curve, and the ones with white around it are the errors on either side.
Do you have a picture for glucose?
No, this is just the predictor space. I'm just showing you how the model sees that data. A random forest sees it like this. So totally different representation of the data, of that data. Where again, X is the same glucose and Y is BMI, and I picked those two specifically. A GLM net is a line, so it draws a line, and deep neural net, ignoring all this stuff, going to the bottom, draws in like a kind of couple curves here, and so it's learning a different relationship altogether, but same data.
Yeah, but it has a lot more circles up in that part of it.
Yeah. So and there's things you could tune, which this is not a tuned neural net. This is kind of the first out of the box thing. It's actually only 2 deep, so it's not even that deep of a neural net. But with so few predictors, you wouldn't necessarily think you would need a deep neural net to do modeling. You might actually overfit by contorting into a position that doesn't generalize well, but fits the training data well. And then, the other question comes up is, how much data do I need? Have I gotten all the data I need? And this is called a learning curve. So you take different percentages of your training data and actually see how well you generalize. And so you can see that pretty much once you've gotten to about 50% of your training data, your accuracy is kind of leveled off. So if this curve looked like this, then you would actually go back to whoever it is you're going to go back to and say, I need more data. Because my training performance has, I'm still getting better and better and better. I think I'll get even more better if you can give me more data. But here it looks like, and usually, and even like with 20%, you're in a reasonable accuracy range. These are the 2 of the different models that I just showed. But this is something you can do to figure that out. So that's all I wanted to show today. I realized we're a little bit over time.
That was good.
But I look forward to kind of interacting with you, and feel free to reach out if you want to just chat about what you're doing or are looking for things to do.
Great.
Thank you.
Good.
Quite interesting.